Okay, hello everyone. In this video, I'm going to introduce symmetric groups. Those are also known as the group of permutations. Okay, um, and possibly I will introduce the cycle notation of a permutation. We will do some interesting problems related to uh, the order of a permutation, and possibly, if possible, if the video length is not too long, I will also cover alternating groups. Okay, let's get started. Okay, now we all have seen this particular notation. You might be familiar as SN, right? This is the notation we use for the symmetric group of for the symmetric group. This is the particular notation we use for the symmetric group. If you notice, what does it actually do? It is the set of all permutation. Okay, this is basically the set of all permutations on the set on 1 2 of the integers 1 2 all the way through n, right? So that's what we call the set. That's what is the group, symmetric group. I said that's what. Now this is the basically this is what to tell you. This is what I would have to say. The elements of the group. These are basically the elements of the group, the permutations. Now here, what we will you have to change your perspective on how permutations are viewed. Of course, I have not yet talked about the group operation. Okay, to understand the group operation, you have to change your perspective on. You have to change your perspective about permutations in general. You have to look at them as functions. Okay, suppose consider a permutation text. A permutation is a function. A permutation is a function. A permutation of Jn. Okay, let's call the set Jn. I mean, this set is often called Jn in analysis. 1 through n. Okay, a permutation of the set. Okay, is a function f, or usually we use the letter sigma to denote them. Okay, that's better. Is a function Jn to Jn, which is bijective. Okay, or which is bijective. That is, you have a one-to-one correspondence from Jn to Jn. As an example, you can say, let's say, take as an example, as a simple example, let's take n is equals to 3. Okay, n is equals to 3. You could say you could define a permutation sigma, which goes 1 to 2, 2 to 3, maybe 3 again to 1, which is left, right? So that's a bijection from J3 to J3. I guess you can see that, right? Now in the general term, the way we were introduced to permutation in likely in probability or other problems is that in the number of ways in which you can shuffle around 1 to 3, right? The ways in which you can shuffle around 1 to 3, right? You can see that it's basically the same. Now you can of course say 1 through 2, which corresponds to the function sigma, which corresponds to the function which maps what I would say one should be there which fixes everything, right? 1, 2, and 3, which is the original, okay, which is just sigma of 1 is equals to 1, and sigma of 2 is equals to 2, sigma of 3, which basically fixes everything in its place, right? So that's one of the permutations. Now another one here. Now you could see this, the argument of sigma is basically, you can think of that as an index, okay? Now think of this as an array. You will understand that the second position is a 3, so sigma of 2 is equals to 3, and sigma of 2 is equal, sigma of 3 is equals to 2. That's all about it, okay? So that's a function, right? So that's, you have a function here. So sigma is a function which maps 1 to 1, 2 to 3, and 3 to 2. Similarly, you will have maybe 2, 1, 3, maybe. That's another function possibly, which will map sigma, which will map, or in other words, I should change the notation. It maps to this notation. Should get familiar with this notation as well. It maps 1 to 2. That means the first position is given to 2, right? And then the second position is given to 1. Think it in that manner. You could say that the second position is given to 1, right? So it maps 2 to 1. That's the point. Next, 3. And the third position is given to 3 only, so it's fixed, right? So 3 is a fixed point of our permutation. Okay, next we have maybe 2, 3, 1, possibly 2, 3, 1. What does that do? It maps 1 to 2, because the first position is given to 2, the second position is given to 3, and the third position is given to 1 again. So that's all we have about it. And of course, you can see next, I think we can have 3, 1, 2 maybe. 3, 1, 2, which is just the implication. The implication is not that serious, don't worry. Okay, I just wanted to mean equivalent instead of implied. Okay, but whatever, it doesn't matter. See, the first position is given to 3, the second to 1, and the last one to 2. There are no fixed points in this permutation. Everything is shuffled, right? Next is what? 3, 2, 1 maybe. Try that. 3, 2, 1. You should get, 1 is mapped to 3, of course. 2 is the position which was originally held by 2, remains with 2, so that's a fixed point. And the last position is, of course, given to 1. That's it. So these are the 6 permutations. You can't have more. These are the ways you can shuffle the objects. Think of 1 to 3 as objects, and you have shuffled them around. Just like a deck of cards, you can shuffle it around so that the relative position of each card changes with respect to the other cards, right? So in the similar manner, 1, 2, 3 are objects which you have shuffled around in various ways, right? That's all about it. Now this is about, I hope that you have learned to think about functions, think about permutations as if they are functions, right? The number, the size of the group Sn. Okay, as I told you, Sn is the set of all these functions, okay, of all these functions which bijective functions from Jn to Jn, okay. Let me write it again. Sn is equals to f times sigma Jn. Sigma is a function, Jn to Jn, such that sigma is bijective. That's about it. Such that sigma is bijective. No need to worry about it. So let me redefine. That's how you can define it. And of course, the size of the group Sn is equals to n factorial. You can of course derive this with very easy, a combinatorial argument. That's very easy to derive using combinatorial argument. You could argue that there are n objects. The first object can be placed in n ways, right? There are n positions for the first object, okay, and then the second object has n minus 1 options because one of the places, suppose, okay, let me speak. Okay, I think I am lost here. If you have lost me, don't worry. Imagine there are 10 empty chairs and 10 people have to be seated. So in how many ways could you do that? The first person in the queue will take any one of the 10 seats, okay? So he could do that in 10 ways, right? The second person in the queue will have 9 options, right? Because one of the chairs is already occupied. So and so on until the last person in the queue. He won't have any option. He would have only one seat which he has to occupy. So if you multiply 10 times 9 times 8 times all the way through 1, that's basically 10 factorial. Okay, that's an intuition why we get the size of the group Sn to be 1 to be n factorial. Okay, every bijective function from Jn to Jn has a one-to-one correspondence with some permutation of Jn. That's what I mean to say. Okay, now just don't confused. I hope it's clear. Now, why do we need this? What I was talking about in the beginning, the cycle notation. Why do we need it? Okay, now in reality we could write this even more precisely. Now before the cycle notation there's one more famous notation called the matrix notation. Okay, I mean it's also written in matrix form. Okay, how will you do that? Here you have two rows, one for the inputs, another for the outputs. Okay, so 1, 2, and 3. I will just copy this up because I will need this. So 1 is mapped to 1, 2 is mapped to 2. Here's the inputs, these are the inputs, and these will be the outputs. Okay, and 3, that's the fixed permutation. Okay, because every point of this particular permutation is fixed. So it will kind of work as the identity of our group. Though I have not yet talked about what the group operation of Sn is, of the symmetric group is, but I will do very shortly. Wait a minute. So 1, 2, 3, and now suppose you have shuffled around 1, 3, and 2, right? That's what you get. Your 1 is mapped to 2, 2 is mapped to 1, 3 is mapped to 3, and then again here 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 1. I hope it's clear. 1 is mapped to 3, 2 is mapped to 1, 3 is mapped to 2. Maybe it's correct, right? Next 1 is mapped to 3, 2 is mapped to 2 because that's a fixed point, and 3 is mapped to 1. That's the matrix. That's how we put it in matrices. Okay, that's also a popular notation I've seen in books. Okay. Now basically, what's the group operation? Okay, basically the group operation of this set of functions, that is the symmetric group, is basically function composition. Of course, you know, function composition is associative and it is not commutative. Of course, you know that function composition is not commutative generally. And of course, since every function here is bijective, you know that an inverse function could be easily computed, right? You can always compute an inverse function of a bijective function. Especially here the domain and the codomain are finite, right? A finite set. So it's not much to worry about. Okay. So it satisfies all the criterions which a group requires. So it's indeed a group under the function composition types is a group under function composition, and of course, as you have seen, the size of the group is given by n factorial. Okay, I hope that's pretty much clear. I've discussed why that is the case. Okay. Now, of course, how do we do it? Now, how do we write in the famous cycle notation, using the famous cycle notation? How do we do it? Okay. Now look at it. Now this basically is what I would say. Everything is fixed in here. Okay. So the cycle notation, you should read the cycle notation here. 1 is mapped to 1. So we just open bracket, close bracket indicates a fixed point. Okay. And then we close. All the points are fixed. This is what we indicate through that. This is what we indicate through with open bracket, closed bracket, a single letter in it, a single digit in it. That's what is indicated by this notation. Okay, that because it's a fixed point. You read. I will read it as 1 is a fixed point of the permutation. 2 is a fixed point. Every point is fixed, so we write every point within the brackets, within parentheses, right? Okay. Now look at here. 1, 2, 3. Now 1 is mapped to 1, so 1 is of course a fixed point. And then look at here. 2 is mapped to 3. So we'll write 2 adjacent to 3, and then you see 3 is mapped to 2. Now the fact is, when we close the brackets, it's kind of a roundabout, you could say. The last member of the parentheses goes and maps to the first member. Okay, that's about it. So 2 is mapped to 3 indeed, because it is adjacent to it, and you can assume the last member is mapped to the first member. That's a rule, you could say, convention. Sorry, there's no point 4, so this is about it. Okay, now let us see here. Of course, you could see 1 is mapped to 2 and 2 is mapped to 2. 2 is mapped to 1, so you see 2 will be back and mapped to 1. So 1, 2 itself, and 3 is a fixed point. Okay, now let us see here. 1 is mapped to 2, 2 is mapped to 3, and 3 is mapped to 1. I think nothing is fixed, right? So this will be a fun problem. You could see 1 is mapped to 2, and then 2 is mapped to 3. They will just place 3 adjacent to it. And then 3 in turn is mapped to 1, you could say. Now 3 in turn is mapped to 1, so it will just close it. That's about it. I hope the notation becomes more and more clear. You need to solve a little bit some problems in order to make yourself familiar with this notation. Okay, let us see more. In this case, we can see 1 is mapped to 3, so we'll write 1 and 3 adjacent, and then you could see 3 is mapped to 2 again. Okay, the question is, why did we skip 2? Why did we skip 2? Don't worry about that. Since 1 is mapped to 3, the next question we will ask is that where is 3 mapped? Because the adjacent thing, that's the domain, that's the demand of the adjacent letter, right? We will write the next thing adjacent to it. The question is what we will write. Well, adjacent to 3, the thing which is mapped to 3, right? If it had it been 1, we would have closed the bracket, correct? But since it's not 1, it's 2, we need to write 2. Okay, now that's about it. So we have all the points have been dedicated, because you could see you don't have to check that 2 is mapped to 1, because that's the only position which is left. That is the only thing which is to be mapped to. What I'm arguing is that since 1 is mapped to 3, 3 is mapped to 2, it's by default, it's automatic that 2 will be mapped to 1, because it's bijection, right? So you can see 2 is mapped to 1. That's it. Okay, now let us look at here. 1 is mapped to 3. Okay, we'll see that 1 is mapped to 3. So 3 will appear adjacent to 1, and what will appear adjacent to 3? 3, 1. So 3 is again mapped to 1. So we'll just close it because 3 is mapped to 1. Now this 2 cycle, okay, these individual things are called cycles, which we write within parentheses. This is a cycle. Okay, this is a cycle. this is a cycle. This notation is often called disjoint cycles. What do we mean by disjoint cycle? Is that no two cycles written in the product. Okay, it's, you could think of this as product of cycles. So one is a cycle, and 2, 3 is another cycle. We have multiplied them. We could think it in that manner. Okay, the no two cycles in a product share anything in common. You could see these two share 2 and 3. This shares 1. This cycle has 1. So the cycles are mutually exclusive. Okay, that's what I mean. That is, you could say they don't share anything. So they are called disjoint cycles. If two cycles don't share anything, they are called disjoint cycles. And you'll learn more about them all soon. Okay. 1, 3. So here we go 1, 3, and 2 is a fixed point. So we'll just write it within parentheses here in this case, because 2 is a fixed point. 2 is not to 2. Now the thing is about this cycle notation is that we usually don't write the fixed points. Okay, we simplify. The fixed points are redundant. Okay, if a point is not written, we consider it fixed by default. I'm sorry. Okay, we consider it fixed by default. Now, since all the points are fixed in this permutation, we will just do this. This is the usual notation, because of course if you write nothing, it does not make sense. So we usually use this, or often the symbol I think or the ID is written. Okay, the words ID for identity. This is called the identity because everything is mapped to one side. Every digit is mapped to itself, right? And this is basically 2, 3, because we won't have to write the fixed point, that is 1 in this case. Okay, now this 2, 3 in particular is called a transposition. Okay, I will come to later while it's a 2 cycle is called a transposition. Now you have to understand what it means visually to get the significance of this thing. Okay, now this is similarly 1, 2, because the fixed point did not written. Now 1, 2, 3, you can simplify this because all the points have, because there are no single cycle or fixed points, right? We don't have to write fixed points. So 1, 3 again. That's it. So these are the simple notations. That is ID. That is for ID for identity. 2, 3 a transposition. Then again, if you have difficulty with this term transposition, call it a 2 cycle. 2 cycle means a cycle of length 2. Here you see how many atoms are there in this cycle. 2. You can count them, right? So that's a 2 cycle, 3 cycle, 3 cycle, 2 cycle. So that makes for the 6 permutations of this group. I hope you have learned a little bit about it, but don't quite worry if this concept is intriguing. But this is a compactness. We do it for the sake of compactness. Instead of writing all this nonsense, 1 maps to 2, or even the matrix notation, which is very cumbersome to write, this notation is very precise, and we can write a lot. We can convey a great deal of meaning through this. Okay. Now, how do we multiply? Okay, I think I should say a little bit more about how the cycle notations work and how to decode them in particular to a particular permutation. Now suppose I'm giving you an example, 1, 2, 3, a good example, 4, 5, 6. Mind that the permutations are all disjoint. That means here we have 1, 2, 3. So that means what? Every number occurs once, okay, in the entire product. What I mean is that every number will occur exactly once. Okay. 8. Now suppose this in S9. Okay. Suppose this permutation takes decode this. Now it belongs to S9, so we'll just rule the matrix. So there will be, I think, 9 columns. So everything corresponding to. Okay, I'll just decode. That is what we did. We'll basically do the reverse of what we have done so far. We'll just reverse that thing. That is, we'll write it in the matrix notation. What is mapped to what, right? That will answer those questions. 7, 8, and 9. Okay, as you can see from here, from this 3 cycle, it is pretty much clear 1 is mapped to 2 and 2 is mapped to 3. So 1 is mapped to 2, 2 is mapped to 3. And then again, 3 is mapped to 1. So that's pretty clear. 4 is, I'll look at the second cycle. Now we are done with this cycle. We will not bother about it anymore because we have written down all the information conveyed by that cycle. Okay. Next, 4 is mapped to 5. That's interesting. So 4 is mapped to 5, and then again you could see 5 is mapped to 8. So we use adjacent means they map. Okay, if 2 items are adjacent, it means that the left one is mapped to the right one. So 5 is mapped to 8. Okay, and lastly, and since this is closed, this 8 will reverse and it will be mapped. In turn, will be mapped to the first item. That is 8 is mapped to 4. That's about it. And you know 6, 7 and 9 are not mentioned, which means what? These points are basically fixed points. That is, they are mapped to, they are kind of, that's about it. So this is the permutation. Okay, and these two are just equivalent. These are just notation, nothing more. Okay, you could say this is just a matter of notation, I would say. Okay, that's just about notation. So don't get confused. This is just a notation for the reverse thing. I hope you could also do the reverse thing. That is of course write the cycle. That is decipher the cycle notation from the matrix notation, and vice versa. These things are pretty easy to do. You just need some practice. I would recommend. We'll just solve some beginners exercises in this topic maybe. Okay, so do try those out. Do follow any book, maybe Hostins. I don't care, but just fix your mind about this particular cycle notation. This is very important. In fact, this is so creative. This is so this makes things much easier to write. You could see the difference. This is just a few. This is just so compact, so nice, so clean. But this is large. Okay, though the meaning is more explicit, the meaning of the permutation is more explicit from the matrix notation, which I've highlighted. But it's not compact. In math, we prefer compact stuff. So this is more compact, and this is more useful. Okay. Now. That's about it. Now how the function composition works. Okay, now suppose you have two. First we'll carry out function composition in what I will say in this using the matrix notation. I'll pick 2 of them from here. Find text, find composition. I think this is the symbol for composition. This composed with the I think this one. Nice. How do I find that? Find the composition. Okay, now we'll do the composition thing and using matrix. First we will do that from matrix. Okay, as you know what happens, you have to think in terms of function. Suppose the function represented by this is maybe this symbol. Suppose the symbol represented by this is pi, and this is suppose this the function represented by this is sigma. We are just attempting to find pi of sigma. Pi of sigma. That's what we are trying to find. How do we find this function? Okay. Now you have to find the value of evaluate this function at different points, right? How do we do that? First we will evaluate it at 1. Now what is sigma of 1? What is sigma of 1? That is 3. That is just pi of 3, which is nothing but, why is 3 mapped here? 3 is mapped to 3, right? So that's 3. Next, pi's composition sigma of 2. We'll just repeat this exercise. You should see sigma of 2 is 2. That's a fixed point. So pi of 2, which is nothing but 2. That's about it. Now, let me repeat that. 1, 2, and 3, the last point, 3. So pi of 3, sigma of 3 is just pi of 1 because I think this. From there you go. And pi of 1, that's just 2. Am I doing it correct? I don't think so. Sorry, pi of 2 is just 1. If you can see from this column, 2 is just 1. I'm mistaken. Okay. So now you know that a pi composition sigma is we just walked out function composition. Okay. It's again a matrix, and you can see we have 3 columns. Now see 1, 2, and 3. Okay, the corresponding outputs are 3, 1, and 2. That's about it. I hope it's pretty clear, right? That's the function composition. Now see if that is available. Try to write it in cycle notation. Okay. Now 1 is mapped to 3, and then again 3 is mapped to 2. Find it in the table. Yep, it is there. So indeed, which is to be expected, because group is closed under its operation. A group is closed under its operation. That's what we know, right? The group is necessarily closed under its operation. So of course, you can see that it's so. If you take composition, you will get a member of this group only, right? So that's what we have seen here. Pi composition sigma, right? I think it's clear. I hope so. Okay, that's how you take composition. Now, how do you visualize composition? The same thing using the cycle notation. Alternately, you could visualize this using the cycle notation. What is the cycle notation for pi? What is the tell me the cycle notation for pi. I think it is 1, 2, and 2 is mapped to, so 2 is a fixed point. We will not write that. And composition, I mean, that's composition symbol. And sigma, 1 is mapped to 3, and then again 3, I think that's about it. 2 is a fixed point, right? These both of them are transpositions. One fixed point. Now, how do we do it? You have to visualize it. It's not hard, okay? It's not hard. Just try to visualize it. 1 is mapped to 3. Now, 1 is mapped to 3, and where is 3 mapped to? And what does this permutation map to? It's a fixed point, right? So in the resultant, 1 will be mapped to 3. Oh, did you get me? Where is 1 mapped to? The first question will be, where is 1 mapped to? 1 is mapped to 3. And then where is 3 mapped to? 3 is mapped to itself, because that's a fixed point of this permutation, of the permutation on the left, right? So that's about, so 1 will be mapped to 3 in the resultant. Now where is 3 mapped to? That's the second permutation will answer. It's mapped to 1. And where is 1 mapped to? It's mapped to 2. So 3 will be mapped to 2. Again, now let us see 2. Where will be 2 mapped to? The first permutation says, it's fixed. So 2 is fixed. So 2 is mapped to 2. And then the second permutation will answer 2 is. So where 2 is mapped to 2, and then again 2 will be mapped to 1. So that's it. We close this bracket. I hope it's clear that the multiplication, now basically the composition is often called multiplication, cycle multiplication, whatever you say. So that's how it works. Of course, if you see another factors, you could always confirm that disjoint cycles commute. Now suppose you are evaluating this in S4. Okay? Suppose this is you are evaluating this in S4. Now since these two cycles don't share anything in common, that is, they don't shuffle around some particular any common point, that means they commute. What I mean is that you could write them in either order. Okay, you could write them in either order. It does not quite matter. Is equals to this. Is equals to 1, 4. If you shuffle, the order doesn't matter because these two don't have anything in common. You can see 2 and 3, 1 and 4. Nothing. There is nothing in common, right? So that's all about it. In fact, we don't even bother to write the composition symbol because it doesn't quite matter. Okay, that's what we mean when we say the two cycles commute. In order to find out whether or not two cycles commute or not, you have to check whether two cycles commute if they are disjoint. Okay, that was the point I was telling. So multiplication becomes easy if you notice that the cycles are disjoint. Okay, that was my whole point. I hope it's clear. Okay, that's about it. Maybe I think cycle. I hope the cycle notation and how the composition works is clear. Let me introduce. And what more should I do in this area? So I hope I think you have understood how it works in background. Okay. I think that's too long for this video. I will just in the next video I will discuss order of a permutation likely. I recommend you do lots of problems to make yourself to make yourself complacent with the notations and all these things if you are new to this. Okay, that's all I wanted to say. Thank you.